Example 5 says, consider a differentiable function f such that f prime of x is equal to negative x squared plus 2x. Use this information to answer the following questions. Part A says, find the intervals on which f of x is concave down and concave up. And so if we're going to talk about concavity, then we need to find the second derivative. So f double prime of x would equal negative 2x plus 2. And if we set that equal to 0 and solve for x, we get x equals 1. Okay, so I'm going to make my little sign chart now. And here is x equals 1. And then I'm going to use the test numbers 2 and 0 for our second derivative. So let's go ahead and evaluate f double prime of 0. And that's going to be 2, which is positive, and f double prime of 2, which is negative 2, and that is negative. So we go from positive to negative, which means that we can come to the conclusion that f is concave up on the interval negative infinity to positive 1, and f is concave down on the interval 1 to infinity. And if that's the case, if it goes from concave up to concave down when x equals 1, then f has an inflection point at 1 comma, and then we need to evaluate f of 1. However, we don't have the original f function right now, and so I'm going to put a question mark there. So, or another way we can say that is f has an inflection point when x equals 1. We can't really give the y value since we don't have the f function. Let's look at part C. Part C says find a function that could potentially be f of x. And the reason that it says potentially be f of x here is that it turns out there's actually infinitely many possibilities for f of x. And let's talk about why that is. So when we're using the power rules, we bring down the power and then multiply that to our term and decrease the power by 1. So if we want to go in the other direction, the opposite of that is that we would increase the power by 1 and then divide whatever we have by that new power. So f of x is going to equal, we have negative x squared, so instead of writing x squared, I'm going to increase the power by 1 and make it x cubed, and divide that by 3, and then plus 2x, and I'll raise the power by 1 and then divide this by 2, and those would cancel out, and so we'd get f of x is equal to negative x cubed over 3 plus x squared. Now, let's just go ahead and take the derivative of that to verify that we did that correctly. So if we take the derivative of this, then I would bring down the 3, decrease the power to 2 here, and then same thing, I'd bring down the 2 and decrease the power by 1, and that would give us negative x squared plus 2x, which matches what we have in the original problem. Now, pause the video for a moment and ask yourself, why did Mr. Kwan say that there are infinitely many possibilities for f of x? If you've paused the video and you've thought about it and you're still not sure why, let me give you a hint. In f prime of x, what if I put a plus 0 right here? Those are still the same thing. Negative x squared plus 2x is the same thing if I add that plus 0 at the end. Well, in my f of x function, I can put plus any number, any constant that I want, because when we take the derivative of a constant, it ends up being 0. So, if I put plus 7 here in my f of x function, it's still going to give me the correct derivative function. If I put minus 4, it's still going to give me the correct derivative function. If I put plus 1,000,000, it's still going to give me the correct derivative function. So I can add on or subtract on any constant I want on the end, and it will still give me the correct derivative function. So that is why there are infinitely many possibilities. I'm just going to put plus c here, and plus c in mathematics in calculus especially, is known to be like plus some constant. So this is our final answer for part C of this question. And that wraps up this section.